WorldPlay, towards long-term geometric consistency for real-time interactive world modeling. So if you're in generative AI right now, you know the holy grail is the interactive world model.
But it always forces you into this impossible choice, right? Speed or memory.
Pick one. You can't have both.
Well, WorldPlay is a breakthrough because it's basically saying you don't have to choose anymore. This is a streaming video diffusion model that it fundamentally solves that trade-off.
And the core achievement here is generating long horizon streaming 720p video at a super smooth, stable 24 frames per second.
And crucially, it maintains that scene coherence. The geometry doesn't drift, even if you walk miles away in the world and then come back to where you started.
So how do they do it?
They cracked it with 3 major innovations. First up is the dual action representation. It very smartly fuses discrete keyboard inputs with continuous camera poses,
Which gives you robust control, but also really accurate spatial caching.
Second, something they call reconstituted context memory. And this is more than just saving old frames. It's about dynamically rebuilding memory with this elegant fix called temporal reframing.
And that's what stops that long-range memory decay and forces the consistency.
And finally, and this might be the most novel part, context forcing. It's a distillation method designed specifically for these memory-aware models. It aligns the memory between a big teacher model and a fast student model to hit that 24 FPS without losing the consistency they worked so hard to build.
Okay, let's unpack this properly. World models are, they're the building blocks for true visual and spatial reasoning.
Oh, absolutely. Think about embodied robotics, learning physical rules, or the next generation of massive, dynamically generated games.
At its core, a world model is trying to autoregressively predict what's next. So the next video frame, or in WorldPlay's case, the next chunk of video.
Right, based on the current state and what the user does. They define this as a next 16-frame chunk prediction.
And the reason this is so hard is that core conflict we mentioned, real-time generation versus long-term geometric consistency.
Exactly. If you go for speed, you have to simplify your model, you cut down the memory context.
And the result is, what, flickering?
Flickering, or you revisit a room and the table you saw is now, part of the floor. That error accumulation is just deadly for long interactive sessions.
But on the other hand, if you prioritize perfect consistency, you need these huge complex memory systems.
Which just kills your inference speed.
Yeah.
And distillation, the usual tool to speed things up, it just doesn't work well in this context. WorldPlay found the path around all that.
So what's the foundation they're building on?
It's an autoregressive diffusion model. Specifically, it's a chunk-wise generation model that's been fine-tuned from a full sequence model. And the architecture choices here are really important. They use a causal 3D VAE and a diffusion transformer, or a DIT, as the backbone.
Why those two specifically?
The DIT backbone, that handles the high-level visual quality, but the causal 3D VAE, that's the key that enables the streaming.
Because it can compress the sequence data while keeping the order.
Exactly, which is essential for processing video in chunks over time, not all at once.
Okay, so let's get into that first big innovation. The dual action representation. This feels like a classic interactive AI problem.
It is. You have these 2 types of input you need, but they seem to be in conflict.
You have the discrete keyboard inputs, your W, A, S, and D.
Right, and those are great for plausible, scale-adaptive movement. Pressing W means move forward, whether you're in a closet or a giant field.
But it's so imprecise. How can the model know your exact coordinates from an hour ago based on a long string of WWDA?
It can't. Not really. That's why you need the other half. The continuous camera poses, the rotation, R, and translation, T.
That gives you the ground truth for your spatial location.
Perfect for memory retrieval. But,
That's fun.
And here's the catch. If you try to train the model only on those precise coordinates, it becomes super unstable because the training data has so much variance in scene scale.
So the solution is to combine them, let each one do what it's best at.
Precisely. The discrete keys are encoded, and they modulate the DIT blocks, sort of like a time embedding. They handle the general motion. But the real magic for the spatial memory comes from the continuous poses.
And they inject those using something called POPE, right? Projected Relative Positional Encoding.
Yeah, and pre-P is just so much better than older methods like array maps because it generalizes so well. Think of the self-attention calculation as 2 separate functions that get added together.
Okay.
The first one, let's call it atten1, uses 3D row P for the video latents themselves. That keeps the visual content inside the chunk consistent.
And the second one, atten2, must be the geometric anchor.
That's it. It uses a projection matrix derived directly from the camera parameters. It anchors the scene in space. So by combining them, the model gets reliable motion from the keys and the absolute precise location from the poses.
Which is absolutely essential for caching those locations accurately.
You got.
So now that we know exactly where we are, the next challenge is making sure the scene remembers itself. This is where it gets really interesting for me. Innovation 2, the reconstituted context memory.
Yeah, long-term memory in sequence models is just a brutal problem. You can't store every single past frame. It's computationally impossible.
And even if you just store keyframes, standard positional encodings like rope-E, they suffer from, long-range decay.
Long-range decay, the influence of a memory from, say, 10,000 steps ago naturally fades because the relative distance between it and the current frame just keeps growing.
So the model starts treating old, important memories as just noise.
Pretty much. And that leads to extrapolation artifacts where the geometry starts to drift. The model literally forgets the structural truth of that old location.
So WorldPlay rebuilds a custom memory context for every new chunk. How does that work?
It's a two-part system. First, there's the temporal memory. That's just the last few chunks, say the last 3, to make sure immediate motion stays smooth.
And the second part is the spatial memory, the long-term piece.
This is the clever bit. It samples non-adjacent past frames, but only the ones that matter geometrically. It calculates a geometric relevance score based on things like field of view overlap.
So if you turn around, the memory of the room behind you instantly gets a high score and gets pulled in.
Exactly. But the core fix that prevents that decay over time is temporal reframing. This is where they, as you said earlier, essentially lie to the positional encoder.
I love that. So instead of using the real massive time gap,
they just discard it. They dynamically reassign new, fresh positional encodings to all the context frames, whether they're from 3 seconds ago or 3 hours ago.
So it establishes a fixed, small, relative distance to all the important memories.
Exactly. It pulls those critical, long-past memories closer in time, ensuring they stay influential. It completely sidesteps the extrapolation problem. It's a stunningly effective hack on the attention mechanism.
Okay, so this brings us to the bigger picture. WorldPlay isn't just high quality. It's interactive, real-time. That means distillation. You have to get your denoising steps way down, from like 100 to maybe 4.
Right, but why is that so hard here? Why does having memory suddenly break standard distillation?
That is the absolute crux of the issue. Standard distillation just fails for memory-aware, causal, autoregressive models. The teacher model you're learning from, it often has a totally different structure. It might be bidirectional or memoryless.
So its view of the world, its conditional distribution, is mismatched with the students.
Totally mismatched. The student is trying to learn from a teacher who is effectively cheating by looking at the future, or just doesn't use the same kind of causal memory the student needs to function.
And the student just learns garbage.
It learns garbage. That's where context forcing comes in as the third big innovation. They solve this by meticulously aligning the memory context between the teacher and student during distillation.
How do they pull off that alignment?
So the student model generates a few chunks using what they call a memory-augmented self-rollout. It's just using its own causal memory. Then the teacher model, which is a bidirectional diffusion model, is given a context.
But it's a specific context. Right. Its context is structured by masking the chunks the student just generated from the student's own memory.
Ah, so you're forcing the teacher to work under the exact same causal constraints as the student, has to use the same historical memory inputs.
That's it. It forces the teacher's distribution to be as close as possible to the student's process, and this alignment is what allows the distillation to preserve that long-term consistency.
So the student can get away with just 4 denoising steps, making it incredibly fast without accumulating errors.
It's basically learning how to get 100 steps of quality in just 4 steps, all while keeping its memory intact.
And that's what gets them to 24 FPS at 720p. I mean, that's not a tech demo anymore. That's a real-time experience. What else did they need on the engineering side to make that happen?
It was a full-stack effort. They used a novel mixed parallelism, combining sequence and attention parallelism, to distribute the workload for each chunk across 8 H800 GPUs.
Spreading the load is key for speed. But what about latency for the user?
That's where the deployment comes in. They use NVIDIA Triton and critically progressive multi-step VAE decoding. So instead of waiting for all 16 frames in a chunk to be finished, they start streaming them in small batches.
So you, the user, see the first few frames while the later ones are still being processed.
Yep. It minimizes that time to first frame and makes it feel immediate. And of course, they use other optimizations like quantization with sage attention and KV caching to cut down on redundant computations.
This all sounds great, but how robust is it? Does it only work for, synthetic video game worlds?
No, and the training data shows that. They trained on a huge data set of 320,000 videos. It's a mix of real-world footage and high-quality synthetic stuff from Unreal Engine and AAA games.
And they specifically included revisit trajectories.
Yes,
Yeah.
they specifically trained the model to handle returning to old locations to maintain that consistency.
And the quantitative results back this up, right? Especially in those long-term tests over 250 frames.
Oh, it blew the competition away. WorldPlay hit a PSNR of 18.94. The same model without context forcing was down at 16.27, and models that lack memory entirely were even lower. It just proves that their memory system is essential.
The generalization looks incredible, too. It handles real-world scenes, stylized cities, even third-person character control.
And the ablations really prove the value of their big ideas. For example, standard Ropey gave a PSNR of about 14. Reframed Ropey, their hack, jumped that all the way to 16.27.
So that's the hard data showing that overriding that natural time decay is the key.
Absolutely. And they showed that with context forcing, if you misalign the memory even slightly during distillation, the student model just fails or produces horrible artifacts. Getting that alignment right wasn't just helpful, it was mandatory.
And the payoff for all this geometric consistency is huge for actual applications.
Massively. Because the video is geometrically sound, they showed they could integrate it with a 3D reconstruction model and generate high-quality, consistent point clouds of the scene.
That's a huge step. You're not just making a video clip. You're creating a structured 3D asset that could be used in production.
And then there's the dynamic interactivity with promptable events. Because it's autoregressive, you can just change the tiny prompt midstream. You can type, a rainbow appears, or it starts to rain, and the world changes on the fly.
How does that not break the visual continuity?
They use a KV recache technique. It refreshes the cache states based on the new prompt, but does it in a way that preserves the existing visual flow. It's truly interactive world building.
So what does this all mean? It feels like WorldPlay has given us a blueprint showing that the trade-off between speed and consistency, it's not a fundamental law. It can be engineered around.
It can. The combination of that dual action input, the reconstituted memory with temporal reframing, and the memory-aware distillation through context forcing, it really sets a new standard for interactive diffusion models.
And while they're already looking ahead to things like multi-agent interaction or more complex physics, the architecture they've built seems incredibly solid.
It is, and it makes you think about the implications of that context forcing method. I mean, if you can successfully distill these complex memory-dependent causal models with a carefully aligned bidirectional teacher, what other sequential AI processes could be sped up?
Like what? Industrial simulations?
Yeah.
Robotics planning?
Exactly. Any complex sequential task that's currently too slow to be interactive, that ability to efficiently transfer complex causal knowledge from a big model to a fast one, that's the challenge we should all be watching next.